Okay, good morning. I hope you have an excellent night and an excellent experience this week so far. We are come back here for the last day of the first week, the conference, and the second week will be some mini courses. And it's my pleasure to introduce Claudio Llosa, who's going to talk about groups with exotic finite properties from complex Morse theory.
Well, thanks for the introduction and thanks for the invitation to the organizers. It's been a great pleasure to be here at IMPA for the first time, and I really enjoyed this conference, and I hope to be back one day. Right, so I'm going to talk about groups with exotic finiteness properties from complex Morse theory, and I'm going to try and give you somehow a general idea of how you can, well, what these are, what are groups with exotic finiteness properties, and how to use complex Morse theory to construct them. But sort of as a motivating example, I will be talking about the following theorem, which, right, most of what I'm talking, or all of what I'm talking about is based on joint work with PRP, and the main theorem, if you're more of a group theorist, is the following, which appeared in two papers, I guess. The second one was actually on the archive before the first one, but now it's published. And it says that given any natural number n, there is a hyperbolic group G with a subgroup of type Fn minus 1 and not Fn. And since we're at a conference about hyperbolic manifolds, and since I phrased this in terms of actual fundamental groups of hyperbolic manifolds, I won't talk too much about hyperbolic groups here, but I will introduce these finiteness properties. Let me just say, sort of, in terms of general motivation for that theorem, hyperbolic groups are a big class of groups that I guess many of you care about and that are very nice. So they all have really nice properties. For instance, they have these finiteness properties Fn for all n, so they generalize somehow finitely generated and finitely presented in a way I'll make precise later. And they have many other nice properties like solvable word problem, linear Dehn function, solvable conjugacy problem, Tietz alternative. And a natural question is, do their subgroups inherit these nice properties? And for some, the answer is clearly yes. Something like solvability of the word problem passes to subgroups. But for others, it's no. And showing that it's no for some property turns out to be challenging in general. And this is one of these theorems that shows that for finiteness properties, their subgroups do not have them in the strongest possible way. So for every n, there is such subgroup of type Fn minus 1, which is not Fn. And so that I don't forget, let me say before carrying on what the history of this is. So the case n equal 2 is quite old. This is due to Ribbs in the 80s. He used small cancellation theory to prove that there are subgroups of hyperbolic groups which are finitely generated. So F1 is finitely generated and not finitely presented. And then the case n equal 3 is also fairly old by now. So this was due to Brady in 1999, who used cut-zero cube complexes and Besvina-Brady Morse theory to prove that there is a subgroup of a finitely presented subgroup of hyperbolic group, which is not itself hyperbolic. And he did this by showing that it's not F3. Remember, hyperbolic groups are Fn for all n. And meanwhile, some more of these examples have been constructed by Lothar and by Kropholler. But what they all have in common is that they use Besvina-Brady Morse theory on cube complexes. And then a couple of years ago, the paper actually was published also this year, but it preceded that work. Together with Bruno Martelli and PRP, we proved that there are subgroups that are F3, not F4. And this was based on the work of Italiano, Martelli, and Migliorini on fibering right-angled Coxeter groups. So Bruno was talking about their work, or at least mentioning it, and we kind of took these ideas and we then-filled a manifold where we get these not finite type kernels like they constructed, but kernels that are F3 and not F4. And somehow, and then n equals 5 and bigger is our theorem. And somehow here, this already contains, as if you've seen the sort of beautiful examples of Italiano, Martelli, and Migliorini and how they are constructed, it already contains a nice blend of sort of real hyperbolic geometry and cut-zero cube complex. So in this dimension, it was already helpful to have something more than just the combinatorial Morse theory on cut-zero cube complexes. And then to push it further, I mean, one may be able to push this further using combinatorial methods, but so far no one managed. So the way we got around this is by using a different type of Morse theory, which is complex Morse theory. And what I want to do is sort of tell you why complex Morse theory is nice when you get it to work and why it allows us to prove that kind of theorem. Now, I do know that a lot of people have a very geometric background here, so if you do not care about geometric group theory, let me give you a second perspective on this theorem, which is, it can be viewed like, the way we prove this is by using complex hyperbolic lattices. And in some sense, the way we prove this, or the actual groups that go into this proof, and our proof can be viewed as some kind of complex hyperbolic version of Agel's virtual fibering theorem for 3 manifolds, except for complex hyperbolic manifolds, there is an Euler characteristic obstruction that means they cannot virtually fiber in a locally trivial way, just like for real hyperbolic manifolds of even dimension. So you can ask yourself, what is the next best thing we can hope for? And the next best thing we can hope for is arguably something like a smooth function to the circle with very nice singularities. And very nice from a differential geometry point of view means more singularities. And ideally, the index of these singularities should be as high as possible, because it means that the topology of the fibers changes as little as possible, at least in low degrees. So, so for the geometers, what we really prove is the following theorem. We show that, yeah. Which one? Oh yeah, I can do this. It's more tedious to write with it. That's why I avoided it. But no, it's fine. I'll happily do this. I thought I'd get away with it. Right. So what we prove is that given any complex hyperbolic lattice, so any lattice in the isometry group, or more precisely the group of holomorphic isometries of the complex hyperbolic ball, which is co-compact, so up to passing to a torsion-free finite index subgroup, the quotient will be a closed manifold, arithmetic, and has the property that it virtually admits some maps to the circle, so its virtual first Betti number should be non-trivial. Yeah. Then there is a finite index subgroup and the morphism from this finite index subgroup onto Z with the following properties. So first, this morphism comes from a Morse function on the level of manifolds. So, okay, we'll produce that so that it's torsion-free, so the quotient is a manifold. And our phi will be induced on fundamental groups, so it's an induced map of some smooth function f on the quotient, so to the circle, which is Morse, and it's Morse in the best possible way. So all singularities are in the middle dimension. I will also recall what this means later, but I guess most people have come across Morse functions in one form or another. And I repeat that for maps to the circle, this is the best thing we can hope for. We know from Euler characteristic that there is an obstruction to having a locally trivial fibration over the circle. So all we can hope for is that there is some finite cover which maps to the circle with a Morse function, all of whose singularities are in as big index as possible, and as big index as possible here means middle dimension. So, and right, so these are complex manifolds of dimension 2n, so middle dimension is n. And this is our morphism, right, and our subgroups of, and these groups are hyperbolic because they act geometrically on a delta hyperbolic space, the complex hyperbolic n space. And our subgroups are kernels of these morphisms. So this Morse theory stuff tells you that the kernel of phi is Fn minus 1. And the L2 number obstruction tells you, or the Euler characteristic obstruction tells you that the kernel is not Fn. And I guess I can say that for the history of this, the case n equal 1 is just surface groups. So this is classical that like you can just sit down and find such a Morse map, and you see the kernel of any morphism to Z is nothing. So it's F0, not F1. And I should say n equal 2. These guys are Kähler manifolds, and there's a work of Delson that describes the first BNS invariant of Kähler manifold, which characterizes finite generation of kernels. And if you throw this together with some work of Matthew Stover, then you get that case, and I guess all other cases are new. Right. So much on the results I want to talk about. Now, let's actually go through and give some more detail on what these things are and why they're interesting. And I said I don't really want to go deep into hyperbolic groups, not more than I've done so far, because I feel like for once it's a conference about hyperbolic manifolds. These are hyperbolic manifolds, complex hyperbolic manifolds, so I guess I don't need to convince you that these are interesting objects to study. What I do want to say a few words about are finiteness properties. So I already kind of indicated what they are and how they work, but let me just give a very proper definition, because maybe some people haven't seen it yet. So G will usually be a group. And given a group G, we can always find a so-called classifying space for G, or an Eilenberg-MacLane space. Which is the following. It's a spherical CW complex with fundamental group G. So it has contractible universal cover, and its fundamental group is G. And the way, probably many of you have seen this construction. Just to briefly recall, how do you do this? Well, you take a presentation for the group, you take a 0 cell, then you glue on 1 cells, one for every generator. And then for the relations, you glue on 2 cells along the words described by the relations. And then you may have some 2 spheres that are not filled, so that they give you non-trivial pi2. But you can fill them with 3 cells, and you can keep doing this, and you'll get a potentially infinite dimensional CW complex that has fundamental group G. And somehow this is a very natural topological object associated with a group in the sense that it's unique up to homotopy equivalence. So if you want to view groups from a group theoretic point of view, a topological point of view, that's really the space to look at. And now, if you think about it a little bit and you look at this construction, you will see that if the group you input is finitely generated, you can do this with finite 1 skeleton. If it's finitely presented, you can do this with finite 2 skeleton. And in fact, conversely, you know that the 1 skeleton generates a fundamental group, and you know that the 2 skeleton gives you the relations in the presentation. So having finite 1 skeleton is the same as finitely generated. Having finite 2 skeleton is the same as finitely presented. And now the higher skeleta, you can view some kind of topological higher finiteness properties. So this motivates the definition that G is Fn is if and only if there's a KG1 with finite n skeleton. So with finitely many cells in dimension smaller equal n. And let me just write it. So F1 is the same as finitely generated. And F2 is the same as finitely presented. And sometimes you can aim for more. You can aim for a classifying space that's Fn in all dimensions, so, and that's what we call F infinity. And, or even a classifying space which is finite, so it has finitely many cells, and that we call type F. So now I hope I grab a good chalk. Let's see. Right, and then sort of the typical groups you come across, at least here, tend to be of type F or F infinity. In particular, all hyperbolic groups are of type F infinity, and they are type F if they're torsion-free. So, for instance, this means that all lattices are type F infinity and type F if they're torsion-free. And okay, you probably saw groups that are not finitely generated. You saw groups that are finitely generated, not finitely presented. What's less clear, because every group is given by a presentation, is whether once we're finitely presented, we're actually type Fn for all n maybe, because somehow all the group theoretic information seems to be in the presentation. And this is known to not be true, and this is quite classical by now, so examples of Stallings and Beery in the 60s and 70s showed that there are sort of fairly easy to write down examples that are Fn minus 1, not Fn for all n. Namely, what you can do is you take a direct product of n2 generated free groups and you map this to Z by just mapping every generator onto Z. So let's say you have generators A1, B1 to A and Bn. And then you take the kernel of this. And probably most of you know is if you take F2 and you map it to Z, well, it's a wedge of circles in topologically, and you get an infinite cyclic carrying, so it will be a wedge of infinitely many circles, so that's not finitely generated. And then to get these higher finiteness properties, you can kind of bootstrap this. I don't want to explain this in detail, but I just want to say that the bootstrapping methods work. One nice argument that is in the paper of Brightson is if you project onto one factor, you get a decomposition as an amalgamated product of SBN or of two copies of the first n minus 1 factors over SBN minus 1. And then you can do some inductive argument because you're gluing spaces along subgroups where, yeah, okay. Anyways, I don't want to dwell too much on on das group because it's really about using complex Morse theory to prove finiteness properties. Let me just say that since, Stallings did this for n equals 3, and Beery did all other n. And let me just say that since then, many more examples of groups with exotic finiteness properties have been constructed with many extra conditions. In particular, notably, there's the work of Biswina-Brady that does sort of homological versions of these finiteness properties and shows that they are different from the homotopical ones. But there's many more. So there's a big sort of field of studying these groups with exotic finiteness properties. And I mean, the second thing I should mention is that from a geometric group theory point of view, these properties Fn are quasi-isometry invariant, so they're interesting invariants in geometric group theory. Now, I want to mainly focus, so if you try to prove finiteness properties, most of the times the hard bit is to show that something has a certain finiteness property. Showing it has not some finiteness property tends to be a little easier for practical examples. So I want to focus on using Morse theory to show that something has some finiteness property, but let me just briefly mention how you would show that something is not of type Fn. So we just find some suitable obstructions, and what would be obstructions to not having a classifying space with finitely many cells in some dimension? Well, one easy obstruction would be that the cohomology in this dimension is not finitely generated, because that just means that every classifying space has to have infinitely many cells in that dimension. And that's just one obstruction that often works to prove that something is not Fn. A slightly fancier obstruction that came up in Genevieve's talk are L2 Betty numbers, and that have been used very successfully in the context of Rifus groups to look at virtual algebraic fibering, so morphisms with kernels with exotic finiteness properties. So, and the key ingredient here is, or sort of the starting point of this, in some sense, is a theorem of Luc from 98, who showed that if you have a group G of type Fn, and you have a morphism onto a free abelian group, infinite free abelian group, and then you take its kernel, and if you know that the nth L2 Betty number of G is non-zero, then the kernel cannot be of type Fn. And that, for instance, works for these lattices, because we know that their Euler characteristic is non-trivial, and we actually know that the L2 Betty number in the middle dimension is non-trivial. So whenever you have one of these morphisms, you do know that the kernel is not Fn. The hard bit is to prove that it's Fn minus 1. Are there any questions to this point? Yes? All lattices are of type F2, in fact, of type F infinity. It's the subgroups that are not. So the point is, uniform lattices up to these properties Fn are invariant under passing to finite index subgroups. So you pass to a torsion-free subgroup, and there the quotient for co-compact lattices is a closed manifold. And that actually brings me to the next point. On closed manifolds, you can use Morse theory to put finite cell structures. Are there any more questions? Oh yeah, I forgot to say, since hopefully all of you had fun yesterday, I was planning to go light on you, I guess. Let's see if I succeed. It's always when people say it's going to be an easy short talk, it's neither one nor the other, right? So I'll try my best. Right, so my third point comes actually to the title. It's how to use complex Morse theory to prove that something has good finiteness properties. And why Morse theory? Well, Morse theory, as you probably all know from primary school of topology and differential geometry, is the way to equip manifolds with cell structures. So let's just recall what a Morse function is. A Morse function is a smooth function to the reals, or sometimes also to the circle. If it's to the circle, it's locally of the form I'll tell you. With nice singularities. And what does this mean? It means that if you are in a critical point, so if the differential is 0, then there are local coordinates around this point. Local real coordinates, which send the point to 0, so that in these coordinates, f is a sum of squares with some positive and some negative coefficients. And the number of negative coefficients we call the index of the Morse function. It's probably too little space for a picture. And Morse functions allow us to put finite CW complex structures on all manifolds. So the way you do this is you embed them into some Rn of big dimension, and then you take a generic direction, and this will be a real Morse function in this sense. So for instance, the classical example people always draw is the 2 torus. You take some height function on it, and then generically this will be a Morse function. And the point is that the index of the singularities tells you what kind of cell you need to glue to get a cell structure on your to describe the topology of your manifold. Namely, you start with a minimum that's index 0, so there you have to glue a 0 cell, and then up to homotopy equivalence, you keep going, you get a disk until you hit a saddle point. The saddle point is index 1, so you have to glue a 1 cell. Say like this, then up to homotopy equivalence, you keep going, and you see this union of 2 circles. You hit another saddle point here, index 1 again, you have to glue a 1 cell. And then finally, you keep going and you hit a maximum, which is index 2, so you have to glue a 2 cell. And that works for any closed manifold, and that's why any closed manifold has a finite cell structure. Now, this is sort of the classical use of, I should say K is the index. And this is sort of the classical use of Morse theory, but there are more modern ways of using Morse theory, I guess, or maybe, I guess they're also old, but there are more sort of creative ways than for closed manifolds, which allow you to prove properties like Fn and not Fn plus 1. Namely, okay, if you start with a closed manifold or a compact manifold, you'll always get a finite cell structure, but you can start doing this with manifolds that are not compact. So you can look at situations like the following. So assume we're in a slightly fancier situation where we have a general aspherical manifold of dimension m, and a Morse function on m. Now we're not assuming that m is compact. And let's assume this Morse function is nice in the sense that we manage somehow to get all indices to like close to the middle dimension. let's say there's some k so that, and k will be small compared to the dimension. So that this holds. And concretely, the situation I want you to think of is the following. It's like we have our manifold m bar from earlier. It maps onto the circle by a Morse function, so something that's locally of this form. And then we take the covering induced by the circle, and we get a Morse function to the reals, which is, I should have said this should be a proper Morse function to make things simple. To the reals, which will now be a proper Morse function, so its fibers are compact. And then we run this machinery, and we see what it gives us. So let's assume the map from M to F covers a map from a closed aspherical manifold to the circle, where this is an infinite cyclic covering induced by the morphism 2s1. And then group theoretically, the point is that since this is the covering induced by the kernel of the morphism, M is actually a classifying space for the kernel. So if we can prove that M has finitely many cells up to some dimension, then we proved finiteness properties for this kernel. So now what does the situation give us? Well, what we're seeing here is the following picture. We have M. We have our map to the reals. And it's a proper map, so a generic fiber will just be some closed manifold. It has a finite cell structure. And now, if we exhaust the real line by intervals, we will be crossing singularities. They are locally discrete. And as we're crossing them in the positive and negative direction, there's some direction to this, but in both directions, this being close to the middle dimension means that we have to glue cells that are close to middle dimensional cells. So what it means is that as we exhaust our manifold M, by bigger and bigger preimages of intervals, we recover it from this finite cell complex here by attaching cells of dimension at least m half minus k. So by real Morse theory, we see that M, which, since M is aspherical, is a classifying space for its fundamental group, is homotopy equivalent to the union of a finite cell complex with some L cells glued to it, where L is at least m half minus k. So with other words, phi 1 of M is f m minus m half minus k minus 1, because we start with finite cell structure and we glue cells of only dimension m half minus k. Now, this is somehow, okay, there are different types of Morse theory. There's real Morse theory, there's kind of discrete Bisfina-Brady Morse theory, and there's complex Morse theory. But they all kind of work like this. You start with some nice phi map to R with a nice fiber where you understand the CW complex structure and it's finite up to some dimension. And you show that when you exhaust the line by intervals, you recover the whole classifying space for some kernel by attaching cells of high dimension. And the difficulty in general is to prove that there is such a Morse map. So that's the challenge. And when you have, and what I want to tell you now next is that when you get complex Morse theory to work, this actually comes for free. Now there's a caveat to this. So getting complex Morse theory to work is not easy. Finding complex Morse maps in general is difficult. But if you do get it to work somehow, then everything else becomes straightforward, and because you get into this kind of situation. So somehow complex Morse theory is really powerful to prove finiteness properties, and I guess And there are more applications of this. I mean, I would be interested to see even more than, like more than our theorem here. In an optimistic world where I would manage all I wrote in my notes, I would give you some more. In reality, I guess, I always know that I write these last few pages and I'll run out of time. But so in theory, there could be more at the end, but there won't probably. But I want you to understand how this case works. And so to obtain this condition, let's say star, we use complex Morse theory. So we use the complex Morse function G, which is a holomorphic map to the complex numbers, or locally of this form, from a complex manifold of dimension m. So it's now real dimension 2m, which is basically the same thing as a real Morse function, except that on complex manifolds we can choose complex coordinates. And we again want that if we're in a singular point of the complex Morse function, there exist local complex coordinates Zi, which are sums of real and imaginary parts, so that locally G takes the form of a sum of squares. Except now we're over the complex numbers, so there are no positive and negative signs. So they really look like a sum of positive squares. Now, how does this help? Well, okay, there are some applications of complex Morse theory where you work straight away with maps to C, but I really want to go show you how this gets us into the real situation. And how do we do this? Well, how do we get a real function from a complex valued function? We take its real or imaginary part. So what happens when we take the real part of such a function? Well, this will now be a map from M to the circle. If we choose a nice M, we may get it to be proper. And how does this map look? Well, in a non-singular point, this will locally look like some coordinate plus other stuff. So you'll still get that non-singular points of G are non-singular points of F. In singular points, you see that if you take the real part of G, well, what's the real part of a coordinate square? It's xi squared minus yi squared. So it looks like x1 squared minus 1 squared plus and so on, plus xn squared minus yn squared. And the point is, this is a real Morse function whose singularity is of index n, and this is an arbitrary singularity of a real Morse function. So all singularities of a real Morse function arising as real parts of a complex Morse function are index n. So this means that if in some way we manage to cook up a complex Morse function whose real part comes from the situation where we lifted a map to the circle, and then we look at, then we're actually in business, and we can show that the kernel of the induced map on fundamental groups to the circle is of type F half the dimension minus 1. Fm minus 1 actually, because here, remember, these are complex manifolds, so they are 2m real dimensional. So, and this kind of observation that complex Morse theory is very powerful has been noted quite early on when, not to study finiteness properties, but to study other things. So it goes back to at least Lefschetz, who, I guess, he didn't do it in that way, but he used the fact that Morse theory on complex manifolds is powerful to prove the so-called Lefschetz hyperplane theorem, which allows you to cut homotopical information in compact Kähler manifold, in smooth complex projective varieties down to lower dimensional subvarieties. It has been used by Milner in the 60s, who used it to study the topology of isolated, local topology of isolated hypersurface singularities. And then it's also been used more recently, and in particular it's been used by Simpson, who was looking really at situations like the local the relative connectivity properties of some fibers of maps to C or R with respect to the total space of situations that are quite close to this. And I guess it's not really, it's more of an application of the viewpoint of Simpson, but Delson in 2010 used sort of the perspective of Simpson to describe the first BNS invariant of a compact Kähler manifold in terms of maps to surfaces. And thus allowed him, so the first BNS invariant characterizes finite generation of kernels of morphisms to abelian groups. So thus already drew some connection between complex Morse theory and finiteness properties. And what we observed is that if you can push this connection further, you can do sort of look at what Simpson did, push it a little bit, and get higher finiteness properties by drawing a similar connection as Delson drew to BNS invariants. Right, so, yes?
Can you say again what the relationship between M and N was?
Thank you. That's a very kind way of saying that I have a typo. That's what you wanted to know, right? If there's an N somewhere here left, it should all be small m's. I don't remember why I used small m, but somehow. Yeah, thanks. Right, so now, as I said, there is a caveat to this approach, and the caveat is that in general it's hard to cook up complex Morse functions, but there are some situations where they do arise, and one such situation is for complex hyperbolic Ball quotients. And in the remaining time, I want to indicate how you come up with them for complex hyperbolic Ball quotients. Are there any more questions? So let's come to the last section, which is applications. As I said, it's probably just one application, which is the proof of the main theorem. Maybe I can say a few words at the end on what other applications there are. So the main application for today is the proof of theorem B and thus of theorem A, which, remember, it says that every compact complex hyperbolic Ball quotient, which is also arithmetic and has non-trivial virtual first Betti number, virtually fibers via a Morse function with singularities of index the middle dimension. So let's assume we're given some co-compact arithmetic lattice with virtual non-trivial first Betti number. And I should say these things exist. For instance, all lattices of the simplest type are like this. Then you can use an argument of Essy-Dieu, which is where arithmeticity is used to show that there's a holomorphic map into a holomorphic immersion to a complex torus. So arithmeticity here is used in terms of density of the commensurator. I don't want to go deep into this. It's just to say that somehow once you what it does is that it tells you once you have one non-trivial map to the circle, or equivalently one non-trivial holomorphic one form, then you get many of them and in all directions, and these non-trivial holomorphic one forms can be put together by integration into the so-called, along curves, into the so-called Albanese map, which is a holomorphic map to a complex torus. And having many of them that are all, whose differentials are all linearly independent, gives you immersions. And so that's a very nice way, I find, how arithmeticity and its characterization via density of the commensurator is used to get some consequences. And thus, right, so this is a theorem of Essidieu. And he shows that up to passing to a finite cover, namely a finite cover where B1 is big enough so that you have all these holomorphic one forms that are linearly independent in every point. You get that the Albanese map is an immersion. So the Albanese map is a map to a complex torus that you get by integrating one forms, which exists for every Kähler manifold. It's automatically holomorphic, and in addition, it's a holomorphic immersion. And the immersion bit is the important bit. Actually, it would be enough if this map is finite. So all I'm telling you now works on manifolds that admit finite maps, so finite to one holomorphic maps to tori. Now, what does this give you? What it gives you is that you can look at holomorphic one forms on the torus, and that's something Simpson was already doing, and you can pull them back. And this will give you holomorphic one forms on your complex ball quotient. And having an immersion tells you that these holomorphic one forms will have finitely many zeros. So the point is that if you take a holomorphic one form on the image, while having an immersion means that it's basically, locally, it's like looking at holomorphic one forms on the image. And if you take one on the image, then its vanishing locus has to be a variety. And then you can show that since you're in a torus, it has to be a complex torus. But complex tori only contain like countably many complex subtori, so up to choosing directions that don't like on one of these complex, whose zero set doesn't contain one of these complex subtori, we get holomorphic one forms on M bar with finitely many zeros. So what this tells you is that there is a beta arising as a holomorphic one form with finitely many zeros. On M. And now what do we do from here? Well, now what we do is we go to the universal cover and we integrate this. And then we get a holomorphic function g. So we pick some base point, we integrate against this base point, the pullback of beta to the universal cover. And this will be a holomorphic function from the complex hyperbolic ball to C with isolated singularity. So they're not quite Morse yet, but they're isolated. Locally, there's only there's a discrete set of singular points. Here, pi is the quotient map from complex ball onto IMPA. And now, the thing is, when you have isolated singularities, holomorphic functions with isolated singularities, by adding a small linear term, you can deform them locally and you get Morse functions. So you make the singularities quadratic. So local deformation, and you can do this equivariantly for the action of gamma, since it's a geometric action. And such local deformation is a complex Morse function. And the point is that if you do this equivariantly, local deformations do not change the de Rham class of your form. So if you have a form that is an integral form or rational form, and then you multiply by an integer, then this form, we're still with Morse complex holomorphic forms. If you take the real part of this, then you will actually be looking at the situation that we had earlier. And if you look at the corresponding form, so the real part of our form beta, then if this is an integral or rational class, then this will come up to multiplication by some integer from a map to the circle. And this is what maneuvers us into the situation where we are actually in this picture here, and we can run this Morse machinery on our map. So I should write something. So choosing beta so that the real part of beta is integral or rational, which we can do without changing these properties, because being Morse is an open condition, so we can deform a bit to get a rational class. And choosing beta so that the real part of beta is rational, the map, the real part of G, descends to a map, a real Morse map with index n singularities from M bar to the circle. And this is our map. Like, this is how we get into this game. And now I explained to you what the rest of the proof is. Like, now we play this game because locally we found a map to the circle on the manifold, which locally is the real part of a holomorphic function. All singularities are index n. We lift it to the infinite cyclic covering, and now from this we get that the kernel of the induced morphism on fundamental groups, so the kernel of some morphism to Z, is of type f half the dimension of the manifold minus 1. What's the half the dimension of the manifold? We have a complex n-dimensional manifold. It's real 2n-dimensional, so it's f n minus 1. And this proves the theorem. And maybe I have time to say a few more words. Yes, in the sense that we can run it on any lattice. I don't think we have an argument to say that there are infinitely many commensurability classes of such subgroups. I mean, there must be, but like, I don't think we wrote this up or have an argument, but I might be misremembering now. Right, so And this method is kind of general in that you just need this finite map to the circle. So in particular, we do get more examples like this. So for instance, if you take the examples of Stover and Toledo, these examples of ramified coverings of complex ball quotients, and you compose them with the Albanese map of the ball quotient, you still get a finite map to a torus. So this will, again, you can play this whole game, and you will get subgroups of hyperbolic groups that have n minus 1 not fn. So, and as we do in the more recent paper, which, since it's not published yet, now has an earlier date. So this main theorem also holds for, I write m hat to give it a different name, but basically for these ramified covers of ball quotients. Which were constructed by Stover and Toledo. So, I mean, while the construction as such is different, it's a bit like Ursula's examples, who did in the real hyperbolic situation take ramified covers of real hyperbolic manifolds that give you some negatively curved spaces, and here you really get negatively curved manifolds. And I see you're standing, so I should come to an end. So let me just say in words, like by using the BNS invariant approach, you get also morphisms to Z squared with kernels of type Fn minus 1 not Fn. And then one can go into the Kähler world, and one can use these complex hyperbolic methods to get Kähler groups of type Fn minus 1 not Fn. So there's like some range of applications of this viewpoint. But yeah, I should stop. I promise to not overrun and to keep it light. So thank you.